and welcome to my talk titled Training Neural Network for Machine Intelligence in Automatic Test Pattern Generator. My name is Soham Roy and I am a PhD candidate of Electrical and Computer Engineering Department at Auburn University in Auburn, Alabama, USA, under the supervision of Professor Spencer Millikan and Professor Vishwani Agarwal. Today, I am going to give you some prior work and motivation for this study. Then, I will explain how machine intelligence is applied to our study. I'll also discuss about the possible directions leading to a formal training procedure of the artificial neural network. I'll discuss mathematical calculations, followed by the proposed recursive training algorithm which makes our ANN an evolving ANN. I will also analyze our experimental results thoroughly. Finally, I will conclude this talk by briefly point out the major contributions of this study and future avenues that may be taken to achieve more interesting results. The Dee algorithm in 1967 established ATPG as a standard method of generating high-quality tests for the logic circuit industry. However, since its introduction, it was noticed that ATPG can have frustratingly long runtimes for some circuits. Numerous later studies lowered ATPG runtime in numerous ways, but since the introduction of BODEM in 1981, the theoretical upper limit of ATPG runtime has remained constant. Let us see an example. For a circuit with I inputs, these I may include scan latches in case of scan-induced circuits. ATPG may need to simulate 2 raised to the power number of primary inputs of the circuit vectors to find a test. Although ATPG algorithms typically find tests without simulating close to this many vectors, this upper bound still exists and is occasionally seen in modern circuits. To avoid this upper limit, most ATPG algorithms employ backtracing subroutines. These subroutines trace backwards through a circuit starting from an objective, such as exciting or propagating a fault, and attempt to find input assignments which accomplish the objective. Multiple backtraces from an objective may be required to meet the objective. But if these input assignments accomplish the final goal, that is find a test for the fault, then at most I input vectors must be simulated, which is nothing compared to the theoretical maximum of 2 to the power I. However, this ideal situation presumes no backtracks occur during ATPG. When the backtracing subroutines reach a circuit input and assign it a value, this assignment may block the current or future objectives. When this occurs, ATPG must undo or backtrack to some previous assignment, which means ATPG wastes time simulating unnecessary input vectors. Beyond BODEM, numerous ATPG algorithms attempt to reduce runtime by creating fewer objectives, but to our knowledge, no studies compare ways of backtracing from an objective. When backtracing, it must decide which direction to go, but choosing a wrong direction may result in a backtrack. To develop a new backtracing strategy, I look towards the technology of machine intelligence. Machine intelligence describes a broad category of algorithms that automatically program themselves through experience. This experience can come from unclassified data which the program finds patterns in, which is unsupervised learning, or the experience can come from a database of training problems with desired outcomes, which is supervised learning, or the experience can come from iterative re-evaluation and adjustment, which is reinforced learning. Recently, International Test Conference ITC 2020 published our research work which shows that an artificial neural network ANN can combine multiple heuristics to guide an automatic test pattern generator ATPG with fewer backtracks than required by guidance from any single heuristic. We are going to reuse the same ANN structure that has a single output neuron and a single layer of hidden neurons, which is sufficient to accommodate the training data volume. Conventional PODEM ATPG applied to hard-to-detect and easily detectable faults in selected benchmark circuits provide training data for nodes marked as success if the backtrace leads to a test, or failure if it results in backtrack. Each entry in the training data pattern comprises of the COP controllability, the circuit depth, and the driving gate type given as a one-hot string on the decision point. Let us try to figure out the motivation of this study. These are the results we obtained from our own work of ITC 2020. Since results depend heavily on benchmark sizes, we chose to normalize plots with respect to ANN-guided backtracing results, which we believe more accurately reflect the goal of ATPG research, that is to reduce ATPG runtime by a factor as opposed to by a constant. Therefore, positive plots in these figures reflect results favorable to the machine intelligence. The results on decreasing backtracks show promising results. We see that for most benchmarks, using the ANN in lieu of conventional heuristics decreases the number of backtracks, often considerably so. As we can also see that the improvement in ATPG performance for some benchmark circuits, including some larger benchmarks such as C3540, C7552, C2670, and C432 did not perform well. To motivate this work, we repeated the work of ITC with minor changes. Firstly, training patterns were generated using PODEM applied to 100 hard-to-detect faults in the three highest depth circuits, that is C6288, C3540, and B05. Secondly, the trained ANN was then used to guide a PODEM applied to the 100 hardest to detect faults in each of the 24 benchmark circuits used in the original ANN, that is ITC studies ANN. This figure compares the total backtracks with those of conventional PODEM using distance and COP heuristics. One difference in our evaluation procedure, as stated in the ITC study, is that we did not include backtracks from aborted faults. We refer ITC studies ANN as the original ANN to distinguish it from the ANN developed in this study identified as the new ANN. The ANN training in the ITC research study was ad hoc and rudimentary. Therefore, this study provides a formal training that may elevate ANN-guided PODEMs at performance. This study examines such a training method. The training recursively uses ATPG data generated from hardest to detect as well as easily testable faults, resolves conflicts in data patterns, example when different ANN outputs come from similar inputs, and discards data that does not improve the guidance of ANN. We believe remedying the outliers just mentioned a few slides before requires addressing several aspects of the ANN training procedure. Our investigation led us into following observations. Firstly, the ANN was trained with ATPG data from high-depth circuits. Since C3540 causes worry, I retrained the ANN with just C3540, but still the ATPG performance of this circuit did not improve. Therefore, I retained the three high-depth circuits for training. Secondly, the training data patterns may lead to increase in training error of the ANN and thus degrade its guiding ability. This is explained in details in upcoming slides. Thirdly, all faults do not provide useful training information, and pre-selection of faults for training may unnecessarily increase the training data volume without benefit. Upcoming slides gives a novel method of training the ANN considering three aspects. That is, the training error of ANN must be kept low by adjusting the number of hidden neurons. Training data from a fault must be accepted only if guidance from the resulting ANN reduces backtracks, and the faults used for training data generation should not restrict it to be hard to detect faults. In fact, a fault provides useful training data as long as it reduces backtracks. And finally, the ANN may enter a zone called catastrophic forgetting when it forgets information contained in a large training data volume. Such consideration in training improvement is worth exploring in the future. To remedy conflicting training data patterns, we collect patterns with identical features into groups and then replace each group by a single representative pattern with common features. Since these patterns are derived from actual ATPG runs, the label of a pattern is either 1 indicating success if it belongs in a backtrace leading to a test, or 0 indicating failure if it results in a backtrack. We count the number of 1 and 0 labels in the group, and the representative patterns label is given in the next slide based on a formula. In this slide, a conflict is illustrated by the sample training patterns in figure where the first three patterns have a conflict. This is resolved in this figure where the three patterns are replaced by a single representative pattern with a label count equals 1 divided by number of label 1s plus number of label 0. That is 2 divided by 2 plus 1 equals 0.67. The algorithm is to develop an evolving ANN-guided ATPG is illustrated in the figure. We select large depth circuits C6288, B05, and C3540 from ISCAS 85 and ITC 99 benchmarks. The ANN structure is same as in the ITC recent study, and parameters such as number of hidden neurons and mean square error are initialized. COP-based PODEM is applied to a set of 100 hard-to-detect faults, and number of backtracks is recorded to be minimized through recursive learning. The training starts by using 50 hard-to-detect faults to generate a training database, followed by ANN training to check mean square error and record the corresponding number of hidden neurons simultaneously. This process continues until mean square error starts saturating and corresponding mean square error and the number of hidden neurons are recorded and the ANN is retrained. The similar process is continued for 100 easy-to-detect faults To evaluate the training, the ANN-guided ATPG is applied to 100 hard-to-detect faults of the same training circuit. If backtrack count decreases, then 100 more hard and easy-to-detect faults are added to the training of the ANN as the number of hidden neurons and mean square error are restored. Discarding the corresponding training patterns from the training database, and another circuit is selected to reiterate the same process until one of the following conditions is satisfied. We kept these conditions to satisfy our need, but one can always change these conditions. These conditions are: the number of backtracks should be reduced to at least 50, at most 100 hard and easy to detect faults should be used for training, and finally the ANN contains at most 100 hidden neurons. The graph shows how the new ANN performs on 100 hard to detect faults across benchmarks as compared to the original ANN. In terms of backtracks, with few exceptions, the new ANN does the same or better in reducing backtracks compared to the original ANN, especially for larger circuits. This experiment used all faults, that is testable and redundant faults, to show the efficacy of guidance by the new ANN using the proposed training procedure. Clearly, the new ANN performs better with fewer backtracks than the original ANN as shown in graph, reaffirming the value of the proposed training technique of this study. The graph has some notable observations. First, C17, B02, and B01 have no reconvergent fanouts and therefore have no backtracks. Of course, there is no scope for reducing backtracks by new ANN guidance. Second, except C1908, C432, C499, B12, and B05, the new ANN exceeds expectations in terms of back performance based on reductions in backtracks. Third, the new ANN is able to reduce backtracks for B09, but the CPU time increases. Possibly, more time per backtrace is used in order to reduce backtracks by expensive evaluation of weights and biases of ANN edges that involves matrix multiplication and computation of sigma function. Fourth, the new ANN heuristic does not perform as well on a few circuits compared to the original ANN, but it still outperformed the conventional heuristics like distance and COG, except in case of C432. Here in this graph, it illustrates that CPU time remains constant for smaller circuits, and the reduction for high-depth circuits is observed, perhaps due to simultaneous reduction in backtracks and backtraces. The contributions of this study are listed. Firstly, a technique to resolve conflicts among ANN training data. Main benefit of conflict resolution is improved ANN accuracy as evident from reduction in the mean square error during training. Secondly, a training technique for selecting faults using a recursive training method that dynamically trains an evolving ANN as opposed to the training with a pre-selected set of faults. ATPG data from a fault is retained only if the trained ANN guidance continues to further reduce backtracks over those from conventional heuristics, that is distance and COG. Both hard to detect and easy to test faults are sampled as opposed to only hard to detect faults in our ITC recent studies results. This prevents the training data from being overwhelmingly failure-oriented. And thirdly, an improved assessment of the quality of the ANN guidance by modifying the backtrack count procedure. I count backtracks only for the faults that are detected or found redundant. Earlier work of our ITC recent study also included backtracks from aborted faults, which distorts the count. This study provides several avenues to be explored. First, our focus was on reducing backtracks, but the performance of backtraces, particularly in reconvergent fan-out-free circuits, can also be improved. Secondly, our exploration for eliminating backtracks has a cost in CPU time. Thus, a sweet spot may be found where the reduction of backtracks would be optimum for minimizing CPU time. Third, finding untestable redundant faults earlier can make ATPG for the entire circuit faster. Fourth, recent work has demonstrated that arbitrarily random circuits can generate limitless training data. Fifth, this study is demonstrated on academic benchmark circuits and not on larger industry standard circuits. The authors believe that the ANN-guided ATPG performance trends are quite promising and likely to scale on a wider variety and large set of designs to show broader capabilities in future. Finally, there may be other features such as scope and those related to fan-outs or reconverging signals that can add to the capability of the ANN. Yet another area is to examine ANN structures beyond the single hidden layer. I would like to end by thanking each and every one for their time and attention. Hope in the future I can give you encouraging results based on this study. The floor is now open for question and answer.
What will do? Every time we play the video?
Yes, so after the video stops, we'll say, okay, the floor, in this video, he himself says the floor is open for question and answer. So then the questions will be posted we kind of ask the same question every day. So
And sir, actually in this time, actually what you should do is you should be kept our site ready with the admin login and going to that survey. Okay.
Yeah.
And like then if you open the survey, you will see multiple queries. I think right now you might not see it. There will be if you want, I can just share my screen and show it.
Yeah. Please share and so.
Yeah, I'll share my screen. Okay, right now I'll show it for test site. But on the D day, we need to be doing it for production site only. So instead of this URL will be changed. Okay, this URL and then easy admin. We need to type in the URL, then load it. Once this is loaded, it will ask for username, password. We need to wait. I mean, this thing we need to you may need to kept login ready before the conference start only.
Yeah.
So this will be VLS ID 2021. Username, password which I shared in
Yeah. Earlier I have.
yeah. Then once it is logged in, so we go to the site admin from here, from this menu to site admin,
Yeah.
and then here you see this forms and surveys. These are the forms and surveys, and here actually right now all these forms which you are seeing is for 18th, okay, yesterday. So what we will do is this list will be changing every day. So we will be adding the list based on the current day event.
Yes.
So
Look
if
the
we
demo list. Look
yeah,
the
yeah.
Demo list.
Because if we have it for all day at once, then it will be confused and it's very difficult to pick up that one. So in the end we'll enable everything, but on that D day actually we enable only for a particular day. So for example, if we select this, there are few people who posted the question. So where exactly this, from where the exactly this question comes is, for example, this is the session 1 which is running, right? Here is a input type box where someone can post a query and they post it. So for each separate session we have a different forms. For example, so before that only we need to have, okay, for third session what will be the name and all, we need to take a note of it, and based on that we will select. So that's why, just to avoid the confusion, I am adding date and also the technical session name.
Yeah.
Yeah, because these things we will have only for tutorials and technical sessions, right? These queries we collect. Okay, so we select this tutorial one, and if you see, there will be lot of queries which was received. So maybe if it is more, you will have multiple pages also.
And
And
that also we require that every 5 minutes we need to, whatever the questions, not presentation for each paper is 15 minutes and 5 minutes is question answers.
yeah, I mean, that will be depends on yeah, and that at that time only we need to switch that. So once the paper video is done, quickly we start the Q&A, and we if you get all these things ready, I mean, before we start the Q&A, just switch between these things just to get the latest data, and then out of these queries, whichever is appropriate, we think we can start asking for the session chair on behalf of these visitors. So we can say there's a question from a visitor delegate called Mahima, and then we can start asking questions.
Okay. We can ask on behalf of the delegates, and that will be answered.
Yeah, session chair. We can ask for a session chair. You I think you need to be, you, as you are the host, you need to be logging in another tab and get these questions ready and start asking. And if there is no question, then we may need to make a few and ask some questions to them. Session chair.
Yeah.
Yeah.
Okay, so this is for each session we have around 5 papers. So mostly.
Yeah.
And all presentation slides are this video minutes are of 15 minutes or is some are,
No, those things need to be shared by Vibhu. I think he will share it by today. that Google Drive where we have all the videos. I think he was editing all the videos. And that's how I think that's how he's planning to edit for 15 minutes only. Let's see. Once it is shared, we will come to know.
Yeah.
Okay.
So from our side, we need to log. I need to log in and see the questions, and then.
Yeah. So how it will work is, usually there will be minimum 4 people in each WebEx meeting. One will be Ishwar from EQTribe, who will be streaming. Okay. What I'll do is I'll just communicate with you guys in the WebEx meeting before I start streaming this WebEx meeting. So I'll just ask everyone, okay, if everyone is ready to go live and all. Once everyone says okay, we are ready to go live and to start playing the technical session of video, then I will say okay, now we can start playing, and then I'll switch to WebEx meeting and start streaming the WebEx meeting. And next thing is here we have another host, admin. This Zalak is session admin, who will be creating this WebEx session and sending the invites to you and also the session chair of that particular session, and then she will be the one who will be playing and stopping the videos.
Yeah.
And then as a host, sir, you will be initially before we start, you can be welcoming that session chair and also asking Q&A. Once
So it's time for second session.
Zalak, that is fine. I know this is first time, right? Sir joined, so we'll just explain him everything. So it will be easy for tomorrow. It's fine, even if everything goes live also, no problem. The next session we can just reduce that video and stop it early, no problem. Okay. Today, as we have 0 visitors, maybe that's why we don't have any forms. Okay. From tomorrow we will have it and do the try runs.
So you want to try it once with your screen, or it's fine?
I think better we try it and keep it logged in forever.
Yeah.
Sir, can you share your screen?
Yeah, let me share my screen.
Yeah.
So I'm sharing my screen.
Good morning, everyone. I am Firaz Hussain. It is my honor to present my research work in the 34th International Conference on VLSI Design. My topic of presentation is a zero point 0.4 microampere offset 6 nanosecond sensing time multi-level sense amplifier for resistive non-volatile memories in 65 nanometer LSTP technology. Authored by Firaz Hussain, Bilal Iqbal and Dr. Anuj Grover. Since every research is built on motivation, we are not apart from it. Physical limitations in scaling of non-volatile memories necessitate alternative ways to increase on-chip storage density. And new generation NVMs offer advantages in terms of speed and can enable replacement of embedded volatile RAMs. Further, storing multiple bits in a single cell enables reduction in cost per bit. Therefore, we studied various essential sense amplifier design techniques such as offset voltage cancellation, double sensing margin, strong positive feedback, etc. to achieve a parallel sensing multi-level sense amplifier for resistive non-volatile memories with faster and stable read operations. First, I will cover basics of the offset cancelling current-based sense amplifier, then design of the enhanced OCCP SA. Thereafter, multi-level sense amplifier design for resistive non-volatile memories, followed by comparison and conclusion. Offset cancelling current-based sense amplifier involves two-phase sensing operation. One is pre-charge phase P1 and second is amplification phase P2. At the beginning of pre-charge phase, switches S1, S2, S3 and S4 are turned on, while two switches DS1 and DS2 are off. The diode connected transistor M1 and M2 provides pre-charge current I pre1 and I pre2 to the bit line and dummy bit line, along with ICEL and IREF. Despite the process variation in M1 and M2, current IM1 and IM2 becomes ICEL and IREF after enough pre-charge time. At the end of P1, cell voltage Vcell and reference voltage Vcell are stored in capacitance C1 and C2 respectively. In the amplification phase, the four switches S1 to S4 are turned off, while two double sensing margin switches DS1 and DS2 are turned on. The introduction of these two switches serves as data-dependent reference generator and generates strong positive feedback. The transistor M1 charges this node V cell with the current IM. At the same time, the switch DS1 will discharge this node V cell with the current IREF. Therefore, the total current difference between node V cell and node Vref will be twice of delta I, where delta I is difference between ICEL and IREF. Simulated waveform for the case when ICEL is less than IREF is shown in the figure. When ICEL is less than IREF, it leads to an increase in Vref that causes lowering of IM1 due to AC coupling behavior of C2. Eventually, this IM1 lowering leads to a monotonic decrease in Vcell, which is shown in this figure. Hence, a combination of double sensing margin and strong positive feedback in OCCB SA result in a faster sensing time. The offset cancelling current sense amplifier holds the high read stability characteristic even in the presence of device mismatches M1 and M2. Here we are explaining this high read stability using case when the reference current is greater than the cell current. In pre-charge phase, current IM1 should be smaller than IM2 in the absence of device mismatch as shown in figure number 3b. Here IM1 is smaller than IM2. However, in advanced technology node, there will be process variations which may lead to a larger IMO and hence incorrect current sampling in pre-charge phase as we can see in figure number 3b. Now at the beginning of amplification phase, Vcell starts to decrease because of the discharging current IREF flowing through the switch DS1. And finally, effect of the strong positive feedback decreases cell voltage Vcell till ground. So the wrong current sampling during pre-charge phase due to the device mismatches will be corrected by the OCCB SA. While state-of-the-art OCCB SA we examined so far offers very prominent merits, but it suffers from the power overhead caused by a clamp voltage which gets aggravated in multi-level sense amplifier design. So we propose a new current sense amplifier structure which is known as enhanced offset cancelling current based sense amplifier, and down the line we will be using the word EOCCB SA, which is combined with a voltage latch sense amplifier that is shown in figure number 4. We can see signals pre and amp have been introduced to control the switches S1 to S4 and DS1 DS2. The voltage latch SA will be enabled by signal SAEN and used to generate the digital signal either 0 or 1 based on the EOCCB SA output VCEL and VREF. The consolidated sensing time Tsyn of the proposed EOCCB SA is given here, where T pre and T amp is the precharge time and amplification time of the EOCCB SA, while TSAN is the time during which SAN signal is enabled. For clarity, a complete sequence of the signal associated with the circuit is shown in the figure number 5. The design has been implemented at 1 volt in 65 nanometer LSTP technology, and 4000 Monte Carlo runs have been done across the entire range of PVT conditions to characterize the EOCCB SA. We ensured the design robustness until 0.85 voltage while keeping the sensing time of 6 nanoseconds. In pre-layout simulation result, we noticed that the EOCCB SA has very low 3 sigma offset for a very wide range of current, that is from 20 microampere to 70 microampere. This is significantly better than other state-of-the-art current sense amplifiers. The EOCCB achieves a minimum of 3 sigma offset of 0.4 microampere for reference current 27 microampere, whereas sensing time is 6 nanoseconds. We designed the layout in a common centroid topology and recharacterize our design. The comparison of pre-layout and post-layout result is shown in this figure number 7. It is evident that the low offset range as seen in the pre-layout result has been maintained in the post-layout analysis, and it achieves same yield as offset cancelling current sense amplifier without a clamp voltage. That is why it consumes much lesser power, which is 59.38 microwatt, while supply voltage is increased to 1.1 volt in fast corner for 125 degree centigrade. In multi-level sense amplifier design, maintaining the faster sensing time and high storage density at desirably small power is of prime importance. Therefore, we can safely assume that the proposed EOCCB SA can be used for multi-level sensing in advanced non-volatile memories. Here we come to multi-level sense amplifier architecture. For parallel bit sensing, we propose a sense amplifier based on a parallel sensing scheme using EOCCB SA. In the design, a cell current concurrently compared against 3 reference current IREF A, IREF B, IREF C, and the 3 output QA, QB, QC are generated. Now these 3 outputs QA, QB, QC are used to determine 2-bit data MSB and LSB using this algorithm number 1, which is shown in figure number 9. Layout implementation of the proposed multi-level sense amplifier in 65 nanometer LSTP technology is shown in this figure. The width of the I/O has been limited to 66 micrometer for a MUX2 layout configuration, and total area required for our implementation is 151.2 micrometer square. In the design, we have used 3 reference current 21 microampere, 33 microampere, and 48 microampere, which lie in the low offset region of the EOCCB assay, as we showed it in figure number 6. To characterize the multi-level sense amplifier design, ICL is varied from 19 microampere to 50 microampere. As offset value of the EOCCB assay changes with reference current IREF, the multi-level sense amplifier will have three offset value, which is summarized in table number 1. In the Monte Carlo simulated waveform, we show that the designed multi-level sense amplifier is stable even in the presence of timing mismatch between pre-charge phase and amplification phase. So the resilience of the EOCCB assay is maintained even in the parallel multi-level sensing architecture. Finally, a post-layout power estimation on the fast first corner at 125 degrees centigrade is performed, and total average power at 1.
Hello, the floor is now open for question and answers.